Hey everyone, welcome back to the lab. 10 days ago, I posted a deep technical analysis of the OpenClaw AI platform, specifically the February 15th build. I am genuinely invested in OpenClaw. The idea of an open agent platform that can natively control your machine, read your texts, and manage your calendar is the future of personal computing. It is incredibly exciting. But with that power comes a massive responsibility for security. In the last video, we looked at the glass cannon architectural risks, things like unauthenticated network exposure, full disk access via iMessage, and external supply chain vulnerabilities. Well, the OpenClaw team just pushed a massive update on February 25th. So today, we are doing part 2. I have analyzed their latest source code, their brand new doctrine called Vision.md, and their GitHub repository metrics. Have they fixed the architecture? Or have they doubled down? Let's look at the data. First, let's look at what improved. If we look at their changelog.md between February 15th and February 25th, they did patch dozens of specific bugs. I verified they closed sandbox symlink escapes, tightened up webhook vulnerabilities, and hardened some input sanitization. This is good work, and it shows the maintainers are active. But as we start digging into the repository metrics and the documentation, a very different picture emerges about how they are handling the hard structural flaws we talked about in the first video. Between February 15th and February 25th, the developers manually closed 3,741 bug reports. That is over 42% of all bugs ever closed in the project's entire history, resolved in a 10-day window. Now, when you see a number like that alongside an AI project, a fair question to ask is, couldn't they have just used an AI coding agent to rapidly write code and fix all 3,700 bugs? Mathematically and structurally, the data says no. Here are 3 reasons why this was a bulk categorization process, not a massive AI-driven code fix. Reason 1, the pull request limit. All code changes, even those written by AI, must be reviewed and merged via a pull request. Over those exact 10 days, they only merged 735 PRs. To fix 3,741 bugs, they would have had to merge roughly 5 distinct, verified bug fixes per single PR 24/7 for 10 straight days. And as we'll see later, many of those PRs were massive new features, not bug fixes. Reason 2, AI doesn't fix architecture. Many of the security issues raised by the community are architectural design choices. But an AI cannot unilaterally decide to rewrite the entire plugin execution model to run inside a sandboxed Docker container instead of the host OS. Those structural flaws require deep human design consensus. Reason 3, the new rulebook. The most compelling evidence is the timeline. During the exact same 10-day window that they enacted this massive issue closure, they also pushed a massive rewrite to their security rulebook. Let me show you. Let's look at the new Security.md. While they were rapidly closing out thousands of general bugs, they were simultaneously updating their documentation to redefine many of the massive security flaws we covered in the last video as expected operations. If we look at their exact GitHub commit history for Security.md over this 10-day sprint, the lead maintainer pushed a massive wave of updates, with one specific word appearing over and over again. Clarify. Clarify trusted plugin boundary. Clarify host-side exec trust model default. Clarify gateway node trust boundary. Clarify shared agent trust boundary. What does this clarification mean in plain English? They formalized the one-user trust model and added strict new report acceptance gates. They expanded a section called Common False Positive Patterns, formally classifying reports about plugins having too much access as out of scope. They are basically telling users, if you run this on your network, it's your job to secure the perimeter. We trust the plugins, and we trust the host environment. The data strongly suggests they used this newly documented pipeline to administratively close that massive backlog of architectural flaw reports, classifying them as by design or expected behavior, rather than addressing them via code changes. And if you want to know why this matters, you just have to look at the intersection between their newly published Vision.md and their Security.md. In Vision.md, they state that OpenClaw started as a personal playground to learn AI and build something genuinely useful. They explicitly list their current #1 priority as security and safe defaults. But that is where the disconnect lies. OpenClaw does offer a Docker sandbox for the AI to run basic bash scripts. But as their newly clarified Security.md rules explicitly state, third-party plugins, the skills you download from their marketplace, run in process. They completely bypass that Docker sandbox and inherit the host permissions of the OpenClaw service itself. They are actively choosing not to sandbox third-party plugin code because doing so would fundamentally break the tool's ability to act as a seamless personal assistant across your local files. They are prioritizing the utility of a personal assistant over the structural isolation of a networked application. They want the agent to be powerful, and they belong to a philosophy that believes strict sandbox boundaries for plugins destroys that power. You might have seen the headlines dating back to February 7th. OpenClaw partnered with VirusTotal to scan third-party plugins before download. This is a positive step for catching known traditional malware, but it's important to read their own blog post announcing the partnership. They explicitly state the technical limitations. VirusTotal scanning won't catch everything. A skill that uses natural language to instruct an agent to do something malicious won't trigger a virus signature. A carefully crafted prompt injection payload won't show up in a threat database. This highlights a fundamental mismatch between the security tooling and the actual threat landscape of an AI agent. Because the OpenClaw architecture executes these custom plugins in process with full host access, any prompt injection payload that bypasses the VirusTotal scan has immediate unfettered access to the local file system. They are successfully scanning for traditional Trojans, but the architecture remains highly vulnerable to AI-specific manipulation. Finally, let's look at what they were building while they were closing those 3,700 issues. That 10-day window saw 735 PRs merged. That is incredible velocity. What were they shipping? A fully native Android application with a completely new onboarding flow. A comprehensive UI overhaul for automated cron-scheduled jobs. New voice and text panic button shortcuts to instantly abort an unexpected agent action. A built-in package auto updater. And full support for the Mistral provider. These are complex, massive feature additions. This confirms the reality of OpenClaw today. Shipping complex new architectural surfaces is their absolute priority. Stability and rigorous security isolation are currently secondary to raw feature shipping. So what is the conclusion of this February 25th audit? OpenClaw is fundamentally engineered as a powerful local assistant, not a secure multi-tenant enterprise application. The deployment environment is the perimeter. Plugins have full host access by design. If you want to run this, awesome. It is an amazing piece of technology. But you must use aggressive network segmentation, strict access controls, and understand that you are running a glass cannon. Thanks for watching the lab. All my documentation, the OWASP mapping, and the exact GitHub searches are linked in the description below. Stay safe, and I'll see you in the next review.